All right, so we finally come to the most practical of all the gas laws, because this is the law that governs, well, something that you do every day that sometimes socially can be an awkward situation. Flatulating. That's such a dull, uneducated word. Flatulating. So let us use Phoebe as an example. Okay, so Phoebe is experiencing a tightness in her colon, a pain, and she's holding it because she'd rather be alone when she releases that pressure. Okay, so she's holding it for the sake of Marie and Grant and Maxine and quite possibly Morgan over there, depending on the yes. She wants to hold it, but finally the cramp has become so harsh that she either is going to have to ask me, no, Alec. Ow. She's going to either ask me to be excused, or she's just going to have to let it go. Like that. So,
that was wrong.
You will take care of that after class. Phoebe. So Phoebe, and we are all human beings here. We know what I'm talking about. There's ways in which you can ensure that there is a sound, and there's ways in which perhaps you can't ensure, but you can at least increase the chances of it being quiet. So she does. She uses a technique which she's familiar with, which we're all familiar with, for making it as quiet as possible. And then she begins to pray to whatever deity she worships that it is mostly water vapor and methane, because that is what most of our flatulence is. If it has no odor, then it's just methane and water vapor. Okay? So she begins hoping beyond hope that there's no H2S, dihydrogen sulfide, because that is what puts the stink in flatulence. She smells it. Then she begins to hope that Graham's law is not in effect, and that it's just going to stay around her, and that she can very quickly breathe it all in and hope that no one smells it. But no, folks, Graham's law is in effect. And basically what Graham's law states is that it's going to move along with all the other gases from areas where there's a lot of it to areas where there is not as much. Okay? Sit up straight. Why are you slouching? My gosh. All right, everyone does this. It's okay. Don't be so ashamed. All right, so basically it's radiating out like an explosion, okay, out of here. So, no, if you can smell it, give them a couple of seconds. They're going to smell it too. Now, you got to be cool about this, because you don't need to acknowledge it, because everyone knows that whoever acknowledges it first dealt it. That's right. Okay? So the best thing you can do, Phoebe, is look at Grant, because eventually he's going to acknowledge it, and then blame him for it. Okay? It was Grant's fault because he acknowledged it first. That is Graham's law. Basically, Graham's law tries to describe what happens when you have gases and they're diffusing out. Who goes faster than who? Let's see if Hank Green can explain it some more.
Welcome to another edition of Crash Course today.
What is that smell?
Oh, thanks for the rotten eggs. Who is this? Why are we doing this? I mean, are we going to be using this to illustrate some kind of scientific principle? Because we probably could have, used, some lilacs or something that wasn't egg. So, we're saying, I can smell it when I'm this close, but if I were farther away, I couldn't smell it. Now, eggs produce hydrogen sulfide when they start to go bad, which smells like sulfur. That's what we think of when we think of the sulfur smell. It takes time for the molecules of hydrogen sulfide to make their way to my nose, because obviously gases don't travel from one place place to another instantly. It takes some time, since as we've learned over the past couple of weeks, gases have real-life constraints on how they move here in the non-ideal world. These are the rules that determine, say, how fast a leaking tire goes flat, or why helium balloons don't last forever, and of course, how, where, and when we smell stuff. One key to understanding the behavior of a gas is its velocity, that is, the speed and direction that it moves, and that depends on a few important physical factors. You ready to learn more? Let's do it. The smell is coming from the eggs, isn't it? As with most things in chemistry and also in life, how a gas moves is more complex than it at first appears. The individual particles in a gas never move at exactly the same speed or direction for very long. Instead, they bounce around like crazy, bumping into the walls of the container and each other over and over. It's sort of like a group of kids in a hallway. They may be moving fast individually, but they bounce around a lot and get sidetracked. They always make it to the lunchroom eventually, but the group's overall speed is lower than the speed of any individual kid. So, process is called diffusion. Now, it's important to keep in mind that the particles in a gas don't work together somehow to move in a specific direction. Remember those kids making their way down the hall? They all know where the lunchroom is and they're hungry, so even though there are a lot of distractions, they move purposely toward their destination. Gases, on the other hand, only appear to move in a specific direction. It's really just random collisions pushing the molecules apart, thus making them spread out in every direction. In other words, the gross eggy gas that I smelled earlier didn't travel just toward my nose. Its particles spread out in every direction from the eggs, and my nose simply noticed the ones that happened to have spread in that direction. Because diffusion is completely free movement, calculating the motion of individual particles becomes even more complicated. Now, we're not going to get into the super complex mathematics of all these collisions, but it is possible to make decent estimates regarding the net velocity of gases simply by disregarding the collisions and applying Graham's law of effusion to diffusion as well. Here's that.
Okay, I just passed out to you the review sheet through gas laws. Folks, you have 10,080 minutes to get that done. 10,080 minutes to get that done. Okay? Well, I'm assuming that you're going to work some sleep into that as well. But 10,000 minutes to get that done. Don't forget that. It's due next Monday. So basically, assuming a gas is ideal, how fast a molecule depends on what? Let's have a race now between Ryan and a fun-sized person such as Natalie. Okay. Now, the race begins over there. I hear that the English wing on the CS side of the building is the most congested in the entire. Okay, so the race will begin by Mr. Fowler's room over there in the beginning of the English wing at 2:59 on Friday. Okay, and they have to make their way down to my classroom. They have to go through the CS and down those stairs and then come into my classroom. Who is going to win the race?
I'm going to win because I can push people out of my way.
Yes, Ryan will definitely be able to push through people, bounce them, collide with them, annihilate them. Okay, but Natalie will be able to fit in between the cracks, between people's legs. She'll be able to flitter and flutter and avoid collisions. And because she can avoid collisions, Natalie will win the race. She will win the race. And that is Graham's law. Size does matter. Don't let anyone fool you. Size does matter. The smaller you are, the faster you are in the gaseous realm. What is the easiest way to quantify size? Formula mass. Formula mass. Why is it that the smaller the gas, the faster it will move? How many times will Natalie collide compared to Ryan? A lot less. Here's a practical example.
works. This is a simple acrylic tube, nothing fancy. On one side we have a cotton ball that's soaked with concentrated ammonia, and on the other side a cotton ball soaked with concentrated hydrochloric acid, which is why we're doing this in a lab and not at my desk. Both of these substances are very smelly because they're giving off lots of fumes, or in other words, a lot of the molecules in the liquid are being released in gas form. When we put the cotton balls in the glass tube and close off the ends, those gases continue to spread, but now they have nowhere to go except farther into the tube. Fun fact, ammonia and hydrochloric acid react together readily to form a solid.
Okay, let's look at that equation very quickly. What's wrong with it?
It's not balanced.
Okay, it should be balanced, but it's not balanced because there's something wrong with it.
You can't react to gases.
Yes, you can.
They were in liquid.
No, they were in gaseous form. They were in the cotton ball. The cotton ball was going to let their gases escape. Come on, gang. What's the formula of hydrochloric acid? HC. What in the world were they thinking? Here is a definite typo in Crash Course. Somebody wasn't editing this. Okay, so you have in one corner, weighing a whopping 17 grams per mole, ammonia! In the other corner, big, honkin', monstrous HCl weighing 36 grams per mole. Let's see who's going to win the race. Now remember, they're placing them on opposite sides.
That's a precipitation reaction, but this time it's happening in a mixture of gases, not liquids. Because ammonium chloride is a solid at room temperature, it forms a superfine white powder where the two gases meet in the tube. So we'll be able to tell exactly how far each gas traveled before they met. Let's try to figure out where that's going to be. First though, remember that Graham's law is only an estimate when applied to diffusion, but it's a good enough estimate to work for our purposes here. The molar mass of ammonia...
Now, I'm not going to ask you to use this equation. This is something that you will learn in AP Chemistry. Basically, it's just a ratio. It is the square root of the inverse. So if you want to know who the fastest one is, well, you should already know who the fastest one is. The smaller one is the fastest one. So ammonia is going to equal, how much faster ammonia is equal to the molecular mass of hydrochloric acid divided by the molecular mass, the square root of the molecular mass of ammonia.
Which we call gas A is 17, and the molar mass of hydrochloric acid, gas B, is 36. If we plug those into Graham's law and set hydrochloric acid's rate of diffusion as 1.0, since we're only looking for a ratio here, we'll find that ammonia's rate of diffusion will be about 1.5 times as fast as that of hydrochloric acid. That means that the ammonium chloride should form about 3/5 of the way down the tube from the NH3 and about 2/5 of the way down from the HCl. And there it is. See that white cloud? That's the ammonium chloride powder forming. It'll eventually settle on the glass, but it's so fine that even the tiny currents that occur, the two gases mix are enough to toss it around a little. The ammonia has indeed moved through about 3/5 of the tube. Meanwhile...
Okay, this is hydrochloric acid. This is ammonia. Where did they meet? This is Natalie. This is Ryan. And they crashed right there.
Now the hydrochloric acid has only traveled through about 2/5 of the tube. So we've proven now that...
All right. Place the following in order of ascending diffusion speed. This is what I will expect. Now, Eddie may ask you how many more times faster. I'm not going to ask you that. All you have to do here is, first of all, ask yourself, what does it mean to be ascending? Faster and faster. Okay, so the only way you could know which one is slowest, which one's faster, is by adding them up. C is 12. Plus 4 times 1 is 16. C is 12 plus 2 times 16 is S is 32 plus 2 times 16 is 2 times 16 is... All right, so who's going to be the slowest?
602.
Who is next slowest? Who is the second fastest? And who is the fastest? All right, I'm going to ask you another question. You need to first ask yourself, hey, what order they want me in, and then add them up.
Wait, is it
Go.
Is it really that simple?
It is that simple.
Is that what the song is?
Yes.
Yeah.
14.4, worksheet 14.4, I will expect to be done after this lesson.
Like today?
No, what I'm saying after, you should be able to finish it up after this lesson.
So, did we finish?
All right,
Did we finish?
you're doing this on your own, please.
Did we finish 4.10? It's on this worksheet right here.
4.3, what worksheet is it?
14.10.
That's 14.4, bud.
Oh. Wait, so what you just... Oh, alright, never mind.
Okay, what is it, gang?
I got you. It's H, I mean it's NH3, then it's N, it's O, and it's
NH3 is 17, nitrogen is 28, oxygen is, and fluorine is. Any questions?